Hello everyone. So in this video we are going to review the question 2 from week 1, which is about the interpolation using the Lagrange basis. So firstly, let's try to download these 4 Matlab files from the canvas, and then you can start working with them and try to solve or compute the question part A and B of the question 2. But let's review these files, and we will try to see part A and part B one by one. Before proceeding more, let's see what happens for Lagrange basis. So Lagrange basis, as I said, it's kind of an interpolation. So we want to obtain an interpolation polynomial, which is the summation of yi li. So yi is y data and lix is the Lagrange basis, and the definition of the Lagrange basis is here. So please note that li is different, this index with this j here. Let's see an example here. So we got 3 data here, x0, x1 and x2. So we have 3 data, so we will have 3 Lagrange bases. So L0x, x minus 1/4. So x0 was 1/3, 1/4 is the second x data. So we start, since this is L0, okay, so x1 is this one, 1/4, and x minus 1, and in the denominator, like the definition, xi or x0 minus x1, x0 minus x2. So here. So after calculating L0 and L1 and L2, we are going to multiply them by correspondingly by y0, y1, y2 here. So minus 18 should be multiplied by 2, which will be minus 36, and finally we can multiply, we can obtain the Lagrange interpolation polynomial. Let's go to the Matlab, and here I can create a Lagrange basis, but also you can download it from the canvas file. So Lagrange basis, the name of the function should be as the name of the file here, okay? So the length of the x data is the same as like the number of the x data that we got, x0, x1, x2, whatever. And so with the help of x data, we are able to calculate the Lagrange basis. So let's go back here. This x here can be anything in the interval of the minimum x data until maximum x data. Now, so m can be length of the x. So the x can be, as I said, the interval, that interval. And so we need x data. I is presenting the number of the Lagrange basis, and x can be the interval, which is from minimum of the x data until maximum of x data. Now again, like in question 1 of this week 1, y can be obtained like to be equal 1, okay, or a column vector including just a number 1. And so y can be like y times x minus x data. This is the definition of the Lagrange basis. And notice that this x data, this k shouldn't be equal to, this is definition of this one. There j is k, and so j shouldn't be equal to the number of the bases. Okay, all right. So by this definition, and using this loop we are able to obtain the Lagrange basis. But what is x? So like in question 1, week 1, x, we don't generate a symbolic basis in Matlab, so we need to have some x's as in interval. So now by calculating this Lagrange basis, in order to see the proficiency, we can plot the Lagrange basis, each of them. So let's assume that we have, in fact, we are going to do question 2 part A. So we got x data -2 and 2, and we are going to plot the Lagrange basis. Okay, so we choose the minimum and the maximum of the x data to be equal the interval of the x dot x, and using this function, okay, calling this function, we can call the Lagrange basis and generate the Lagrange basis x data, first x, and since we have 5 x data, therefore we have 5 bases. Alright, so we are able to plot them x, y1, x, y2, and so on. And hold on here, so this will enable us to plot x data and 0. So because Lagrange basis, let's see here, Lagrange basis here, if I put Lagrange basis x equal to like Lix, if I put xj here, this fraction will be 0, so whole Lixj will be 0. Okay, so we will see this plot, and so let's run this one here. So let's analyze this one. We first Lagrange interpolation. This y1 is the blue one, so the blue one will not be 0 in the first -2, but it should be 0 in the rest of the x data. Okay, it should be 1 in x equal -2. So exactly in terms of this definition. All right, so we can see that y4, okay, it's the purple one here, so it's y purple, it won't be 0 in the x data number 4, but it must be 0 in the rest. So therefore our Lagrange basis function, I'm talking about this one, it works perfectly. Now let's analyze this question. It says that consider the script of the plot Lagrange poly. So you can download this one from Canvas, and so now we are going to generate some x data and y data using this function. Okay, so we can use function handle, which you will see in in few seconds, and we will choose 4 equidistant points, which will be so x data for us. So if we choose those 4 equidistant points, we will be able to obtain y data from this relation of the f of x. Let's go there, and question 2b. Okay, all right, so the interval between -1 and 1 here, this one. Okay, the interval is between -1 and 1, and this is the function handle. The way that we are writing function handle is this one: f equal to @ inside the bracket x, distance inside the bracket 12, and the rest of the story, which I just copied from exactly this one. All right, so So we can say that, okay, yv equal to f of xv. So xv was the interval between -1 and 1, and yv can be like this function. All right, so we choose firstly 6 data or 4. Okay, let's choose 4 data from here, and x data can be chosen by this command for equidistant points inside -1 and 1, and y data can be calculated by this command here, feval, by using this function. Let's review this again. Okay, I chose x for equidistant points inside interval -1 and 1. So I have x data inside this one. I can generate y data correspondingly using this one. So I assign x data equidistant points for equidistant points. I sub here and I can obtain y data. Let's go back here. So it's possible to see that y data can be generated by this command line. Now, so we need to use to obtain Lagrange polynomials. What was the Lagrange polynomials? It was, the definition was like this: polynomial yi lix. Okay, we already calculated Lagrange basis. So Lagrange polynomial, we can use a function. We can create a Matlab file, and it is just use the definition of this summation, and this means just we can use just a for loop and obtain it. So let's assume that y is equal 0. Okay, it depends y zeros of this one. Why do we have here like a column vector or row vector? Because x can be chosen like an interval, as in question 1 of week 1. Okay, so y equal y plus y data I. Okay, so y data I times Lagrange basis. It is exactly this definition. All right, and y data is just, as we discussed, the corresponding data from x data. Okay, so for Lagrange polynomials, we need x data as input, y data, and x as, in fact, we need just 2 inputs. But since we are in Matlab, we don't generate symbolic polynomial. We need x, and it is just interval of the minimum of x data and maximum of x data. All right, so let's go back to the question 2b, and ypv, the Lagrange polynomial, can be used this function, and these inputs x data, so which x data has been generated by here for equidistant, and y data is the corresponding x data, and xv is just the interval, which is this, the interval between -1 and 1, minus a and a, but we have assigned a to be equal 1. All right, so we have the Lagrange interpolation polynomial, and we have the exact function, which has been defined by using the function handle. Okay, so we can plot xv, yv, so exact function, and also xv and ypv, which is interpolation polynomial, and also x data and y data to show that our interpolation polynomial, Lagrange interpolation polynomial, interpolates x data and y data. or passes from these 4 points. So let's run this code. All right. So the exact function handle is the red one, which is this one. So this one is 12 times sine 2x and the rest. And the blue one is the polynomial interpolant, which is Lagrange interpolation. So let's do this one. Let's see the exercise. Okay, it says that change the number to 0.5, or we can just use 14 points and increase to the -4 and 4. Let's do this one. So I need to change this one to 4, so the interval will be converted to the interval -4 and 4, and the number of the data 16. Okay, so let's run this one. Okay, now this is little bit close to the exact function. Okay, and we can also test this one, this case. 6 data. Let's do 5 data and 6 here, and 6 data in the interval of -1 and 1. Okay, let's do this one here, and this one should be firstly 5. Let's run this one. Okay, all right, this is this one. Exact function, as I said already, it's the red one, and the blue one is the polynomial, the plot of the Lagrange interpolation polynomial. Let's do this one for n equals 6. Okay, so interpolation, now it looks a little bit closer to the exact function, the plot of the exact function. Okay, so we can somehow conclude that by increasing the number of the x data, we can interpolate the exact function a little bit better. All right, this is the end of the second video for week 1.